Hello students, welcome to P Block Elements lecture 10. In this lecture, we are going to see hydrochloric acid. Now let us see the first concept, that is methods of preparation of hydrochloric acid. The first one, it is prepared by reaction between sodium chloride with concentrated sulfuric acid at 420 Kelvin. So here we are going to get sodium hydrogen sulfate along with hydrochloric acid. This sodium hydrogen sulfate further reacts with sodium chloride at very high temperature of 823 Kelvin to form sodium sulfate and hydrochloric acid as the product. Properties. Hydrochloric acid is a colorless gas with pungent smell. On liquefaction, hydrochloric acid gives a colorless liquid which on freezing gives a white crystalline solid. It is highly soluble in water and highly ionizes in water. When it is dissolved in water, it dissociates, forms H plus and Cl minus. Thereby it is going to act as a strong acid. So hydrochloric acid plus water, it gives hydronium ion and chloride ion. And in this case, the dissociation constant value Ka, that is equal to 10 to the power 7, that is so high that it indicates it is a strong acid. Its aqueous solution is called hydrochloric acid, that we already told. Ordinary concentrated hydrochloric acid that is supplied to the labs is of 37%, that is 12 molar or 12 normal acid. This acid, when you open the lid of that acid, it fumes in moist air and it is called as fuming hydrochloric acid. Sodium burns in hydrochloric acid gas with a bright yellow flame and forms sodium chloride and hydrogen gas. Reaction with ammonia. Ammonia reacts with hydrochloric acid to form ammonium chloride, white fumes. A mixture of 3 parts of concentrated hydrochloric acid and 1 part of concentrated nitric acid is known as aqua regia. So it is used even noble metals like gold, platinum. So it is a mixture that is capable of dissolving almost all metals, including noble metals like gold and platinum. So here you can see the reaction. Gold, that is Rm, reacts with the H plus ion that is obtained from both hydrochloric acid and nitric acid. NO3 minus ion that is obtained from nitric acid, whereas Cl minus is obtained from hydrochloric acid to form a complex of EuCl4 minus plus nitrogen monoxide and water as the product. Similarly, we can write reaction for platinum also. In this case also we are going to get a complex PtCl6 2 minus NO and water as the products. Hydrochloric acid decomposes salts of weaker acids. For example, sodium sulfite, when reacts with hydrochloric acid, it decomposes it to form sodium chloride, water and sulfur dioxide. Similarly, it decomposes sodium carbonate to sodium chloride, carbon dioxide and water. When sodium bicarbonate is treated with hydrochloric acid, it decomposes sodium bicarbonate to form sodium chloride, carbon dioxide and once again water as the product. Oxoacids or oxyacids of halogens. Fluorine forms only one oxoacid, that is hypofluorous acid HOF. It is due to its high electronegativity and small size. The other halogens form many oxoacids. Isolation of these oxoacids in pure state is a difficult task because they are stable only in aqueous solutions. So here we have a table in which we can see different oxoacids. So here we have elements fluorine, chlorine, bromine, iodine. The first type of oxoacid is hypohalous acid, that has a general formula of HOX, where X stands for fluorine, chlorine, bromine, iodine. The first one is hypofluorous acid, HOF, hypochlorous acid, HOCl, hypobromous acid, HOBr, hypoiodous acid, that is HOI. In the case of halous acid, that is HO2X, we have hypohalous acid of chlorine only, that is called chlorous acid with the formula of HClO2. In the case of halic acid, we have chlorine, bromine and iodine are capable of forming it. So chloric acid, that is HClO3, bromic acid, that is HBrO3, iodic acid, that is HiO3. In the case of perhalic acid, we have perchloric acid, HClO4, perbromic acid, HBrO4, periodic acid, HiO4. Structure of oxoacids of chlorine. Hypochlorous acid, HOCl, in which oxidation state of chlorine is found to be equal to 1. Next one is HOClO, that is HClO2, chlorous acid, in which oxidation state of chlorine is +3. Next one is chloric acid, HClO3, in which oxidation state of chlorine is +5. The last one, perchloric acid, HClO4, in which oxidation state of chlorine is +7. Oxidizing power of these oxoacids decreases as the oxidation number of halogen increases. So remember students, it is a hypochlorous acid, that is a stronger oxidizing agent than chlorous acid, that is stronger than chloric acid, that is stronger than perchloric acid. But as far as acidic strength is concerned, the order is going to be reversed. Now let us see thermal stability. Thermal stability increases with increase in oxidation state of halogen. It is a perchloric acid stronger with respect to the thermal stability than chloric acid, that is indeed more stable than chlorous acid, and it is more stable than hypochlorous acid. Introduction to interhalogen compounds. Halogens, when combined with amongst themselves, or in other words, I can say that when one halogen combines with other halogen, the resulting compound, whatever it is going to form, is called as a interhalogen compound. So we have interhalogen compounds of following types: XX dash, for example CLF, BRF, BRCl, ICl, XX3 dash, CLF3, BRF3, IF3, ICl3, XX-5, IF5, BRF5, CLF5, XX7 dash, that is IF7. As the number of two halogens increase in the compound, the possibility of forming that type of compound is observed in the case of halogen with very high electronegativity and the halogen with lower electronegativity. For example, XX7 dash is possible only in the case of iodine fluoride, in which fluorine is highly electronegative, iodine is least electronegative. Here X is a halogen of larger size and higher electronegativity, where X dash is smaller size. Students, here X is a halogen of larger size and lower electronegative, whereas X dash is smaller in size with more electronegativity. X is more electropositive than X dash. Preparations. Formation of chlorine monofluoride. This chlorine monofluoride is a colorless gas. It is prepared by reaction between equal volume of chlorine and fluorine at a temperature of 437 Kelvin. That leads to the formation of 2ClF. Formation of chlorine trifluoride. It is also a colorless gas obtained by reaction between chlorine with excess of fluorine at high temperature of 573 Kelvin. So when chlorine reacts with excess of fluorine, we are going to get ClF3 as the product. Formation of ICl3, it is yellow colored powder. It is obtained by reaction between iodine with excess of chlorine. That leads to the formation of ICl3. Formation of bromine trifluoride, it is yellow green colored liquid. It is obtained by reaction of bromine with water, that is dilute with water. When both of them diluted with water, we get bromine trifluoride. ICl formation, it is a ruby red solid in the case of alpha form and brown red solid in the case of beta form. So it is obtained by equimolar amount of I2 and Cl2 to form 2ICl. The formation of bromine pentafluoride, it is a colorless liquid. Bromine reacts with the excess of fluorine to form bromine pentafluoride. General characteristics of interhalogen compounds. Interhalogen compounds are covalent in nature due to the low electronegative difference between halogens. All these compounds are volatile. Most of them are unstable, but none is explosive. They are diamagnetic in nature. They are more reactive than halogens. It is because in the case of interhalogen compounds, the bond present between two different halogens, that is XX- bonds, are weaker than XX bonds or X-X- bonds. Interhalogen compounds undergo hydrolysis when treated with water. For example, ICl when hydrolyzed, that means reacted with water, it forms chloride ion, hypoiodous acid and hydronium ion. When ICl3 undergoes hydrolysis, it forms ICl, iodic acid and hydrochloric acid as a product. When IF5 undergoes hydrolysis, it forms hydrogen fluoride and I2O5 as a product. Interhalogens like ClF3, BRF3, etc. are very reactive and act as strong fluorinating agents. Interhalogen compounds of the type XX- form addition compounds with unsaturated hydrocarbons. For example, when ethene reacts with XX-, we are going to get an addition product. Interhalogen compounds behave as strong oxidizing agent and attack other elements to give mixture of halides. Structure of interhalogen compounds. Interhalogen compounds of the type XX- are very simple and consist of halogen atoms linked together through a single covalent bond. Thus, their structure can be represented as XX- with a single bond. Structure of XX3-. Interhalogen compounds of the type XX-3 possess T-shaped or trigonal bipyramidal structure. It is formed by sp3d hybridization of the central atom X in its first excited state. See, let us see the structure of XX3-. So in the ground state of group 17 elements, we have general outermost valence shell electronic configuration of ns2 np5. So during formation of XX3-, the paired electron of one of the p orbitals get shifted to the d orbital present in the outermost valence shell, thereby forming 3 unpaired electrons, and along with that we have 2 lone pair electrons. So when all these atomic orbital they combine 1s, 3p, 1d, we are going to get hybridization of sp3d like this, and shape is going to be T shape. In reality, students, the bond angle between x dash x and x dash is less than 90 degree. It is because repulsion between these lone pair electrons with bond pair electrons. So these bonded pair of electrons, they bend and the bond angle decreases than 90 degree. Structure of X5X dash compounds. Interhalogen compounds of the type XX-5 have square pyramidal structure. They are formed by sp3d2 hybridization of the central X atom in its second excited state. So here you can see the outermost valential electronic configuration of halogens NS2 NP5. So now what happens during bond formation in XX5 dash, the paired electrons, they are shifted to the d orbital that is present in the same shell. So now total number of electrons are going to be 5, and there is one paired electron that should be included in hybridization but not in deciding the structure. So hence hybridization is going to be sp3d2. So when I combine all the orbitals involved in hybridization is going to be sp3d2. So it is a square pyramidal structure of xenon pentafluoride. Structure of XX7 dash compounds. The only known interhalogen compound of this type is iodide pentafluoride. It is formed by sp3d3 hybridization of central iodine atom in its third oxidation or excited state. The molecule has a pentagonal bipyramidal structure. Here you can see that along with these paired electrons of p orbital, the paired electrons of s orbital also shifted. Hence total number of unpaired electrons here equal to 7. So all 7 are used in forming single covalent bonds, thereby to form pentagonal bipyramidal structure. So in this case hybridization is going to be sp3d3. Here you can see that pentagonal bipyramidal structure of IF7. Thank you, students.